Hello, welcome to this lesson of the Linear Algebra Tutor. Here we're going to continue working with eigenvalues, and we're going to learn how to solve for and find the eigenvalues of any matrix using the characteristic equation that we're going to talk about. It's very, very simple to do, to write it down. Sometimes it can be a little harder to actually find the eigenvalues, but we're going to show you the technique here. Now keep in mind that typically the way it works is you have to find the eigenvalues first. Then once you have the eigenvalues, then you can go and find the eigenvectors. So what we're going to focus on in this lesson and in the next several lessons is just how to find the eigenvalues. Once we have that locked down, then I'm going to show you how to find the eigenvector. So we'll come back and learn how to do the eigenvector part of it in a few lessons from now. So remember that the eigenvalue problem is ax is equal to lambda x. We've done that and talked about that several times so far. But notice though that I'm going to do some manipulations to kind of show you ax is equal to, I can write this as lambda times ix, where I is just an identity matrix. Remember, an identity matrix is just a matrix with ones along the diagonal. It doesn't really change anything. It's like multiplying by 1. So I can take any equation and multiply by 1. So that's all I'm doing here. And then what you can do is you can take all of these terms and move them over to the left-hand side by subtraction. So you'll get ax minus lambda times ix is equal to 0. So far this is just basic algebra. There's no linear algebra involved in it. I'm just multiplying by 1, I'm subtracting it over. And then finally I can factor out an x because I have an x in both sides. So the way I'm going to do that is I'll open parentheses and I'll say a minus lambda I x is equal to 0. When you factor out the x, you need to make sure and pull it out on the right, because don't forget, these are matrix multiplications. So when you do matrix multiplications in reverse, you can't just really reverse the order of it. So since it's ax and lambda ix, we need to keep the x in the same relative position, so we pull it out to the right. You wouldn't want to pull it out to the left like this. So basically, this is kind of the important thing. You're going to see this a lot. This is basically the eigenvalue equation recast. I mean, this is exactly the same as what we have always started with in the previous couple lessons. We were talking about the eigenvalue problem. This is exactly the same thing. What we want to do is find out what values of lambda make this equation true. We know that there's going to be some eigenvectors that are going to pop into here. That's also the other part of what we want to find. But before we can find those, we want to find the eigenvalues. So what we want to figure out is what values of lambda make this equation work out. What values of lambda make them have non-trivial solutions, in other words. Because don't forget, this is a homogeneous set of matrix equation, right? This is a homogeneous because we have 0 here, and this is a matrix equation on the left-hand side. And don't forget, I told you a few lessons ago, I said it would be important, the test to figure out if a system of equations is going to have non-trivial solutions. I told you that that would be important later, and this is the reason why one reason why it's important. Because I can say this. I can say that this equation has non-trivial. Remember, we want to know the non-trivial solutions because we want to know, we don't care when just everything is 0. We want to know when things are more interesting than that. It has non-trivial solutions when the determinant of this matrix here in front of the variable x, the determinant of a minus lambda I, is equal to 0. This is basically the equation that's going to let us find the eigenvalues, basically. What you need to do is you take the matrix A, you subtract lambda I. I know this looks confusing, but really I is an identity matrix, so it's got 1s on the diagonal and 0s everywhere else. And this is just the eigenvalue here. I'll show you how to write this. You're going to form a matrix with this, and you're going to take the determinant of this matrix and set it equal to 0. And along the way, you're going to be able to find out what the values of lambda are that make this true. The reason that you're setting the determinant equal to 0 is because this is just a homogeneous matrix equation. This is a matrix here. All of this, even though it's got a minus sign, it's just a matrix times column vector x is equal to 0. We already said that it has non-trivial, which means non-zero answers, whenever the determinant of the coefficient matrix is equal to 0. I told you that several lessons ago that would be important. So we're applying it here. And that's why this pops up. Most books won't tell you that. That's why you're setting the determinant equal to 0, but that is in fact the reason why. All right, so let's go over here and do a problem. The easiest way to do it is to do a problem. So let's say your matrix is 1, 2, 2, 1, and we want to find the eigenvectors. I'm sorry, the eigenvalues of this matrix. Okay, what it's telling you is that you want to take the determinant of this weird looking thing here. So let's go ahead and write that down. The determinant of a minus lambda I, and we're going to set it equal to 0. So I'm going to change colors, and I'm going to say the determinant of the matrix. Now, this is a minus lambda I. This is how you do it. You say 1 minus lambda, 2, 2, 1 minus lambda. And you set it equal to 0. Notice what I've done. Everything stays the same. The 2's stay in their locations. The 1's are still here. But on the diagonal elements, I've subtracted lambda. That's all this means. I know it looks confusing. I know it looks weird to have a matrix minus lambda times I. I know that's weird. But this is just matrix A. You're subtracting from it an identity matrix with lambdas on the diagonal elements. So the only place it's going to affect is the diagonal elements, and you'll just be subtracting lambda. So all you do is you take your matrix, you subtract lambda on the diagonal elements, you leave everything else the same, and you take the determinant. Now the next thing running through your head is, well, how do I take the determinant? I've got lambdas everywhere. Those aren't numbers. Well, those are unknowns, of course, but this is a 2 by 2 matrix. You could still do the crisscross method. So going this way, you'll have 1 minus lambda, 1 minus lambda, minus, going this way, you'll have 4, and it's equal to 0. Now notice what we have. We have an equation with only one unknown. We have lambda, and we have it all equal to 0. We can solve for lambda. So let's expand this. The first terms are going to give us 1 minus lambda minus this lambda plus lambda squared minus 4 coming from here is 0. We'll recast everything and say lambda squared minus 2 lambda 1 minus 4 gives us negative 3, and that's equal to 0. Hopefully it'll factor, but even if it doesn't factor, we can always use the quadratic formula to figure out what lambda is. But let's see if it factors. Lambda on the first term, lambda on the first term there. 1 times 3 gives us 3, and then we could put minus and plus. We'll have a positive lambda here. We'll have a negative 3 lambda here. That's going to give us our negative 2 lambda. So this factors. So lambda is equal to negative 1, and lambda is equal to 3. Lambda is equal to negative 1. Lambda is equal to 3. These are the eigenvalues. These are the eigenvalues. So let me go back and kind of go over it a little bit here and label a few things. You don't have to do all this stuff all the time. This was more of a derivation. This is kind of the equation that is exactly the same as the original equation you form. This equation is going to have non-trivial solutions. That means it's going to have eigenvectors that are non-zero when the determinant of this matrix is equal to 0. I've already explained the reason why. Okay? This matrix here, this matrix that you form, A minus lambda I, this thing right here, this is called the characteristic matrix. So basically A minus lambda I. So this matrix here that has the lambdas on the diagonal minus, this matrix is called the characteristic matrix. When you take the determinant and beat it down, you're always going to get a polynomial. This polynomial is called the characteristic polynomial. I'm telling you this because a lot of times in the book is going to talk about the characteristic matrix, the characteristic polynomial, the characteristic equation. And you're like, what does characteristic mean? It's just a word that's used to describe the solution process of eigenvalues, basically. When you get down to matrix form and you get this in terms of a matrix, that's called characteristic matrix. The polynomial that falls out of it is called the characteristic polynomial, the solution of which is called the eigenvalues. Now, if we were continuing this problem, I'd show you how to find the eigenvectors from these eigenvalues. We will get to that, I promise you, but I want to give you a little bit more practice with finding eigenvalues first. So let's go to the next several lessons. We'll get some more practice with eigenvalues, and then we'll hit eigenvectors at the end. Once you have some good practice, I think you'll be able to do that with no problem.